Hello guys, I hope that this video is going to find you in good health. I go by the name of Dambuza and today I am going to do calculus. This is my second video and I now going to focus more on the point of inflation. What is the point of inflation? The point of inflation is the point whereby the graph changes its concavity. So at the end of the lesson, you need to know how do you find the point of inflation using different methods. You need to also be able to analyze the graph and discuss the concavity of the function using the point of inflation. Before we begin, please don't forget to subscribe. 1. Suppose you have the graph of g at x, which is defined as x cubed minus 3x squared, and the graph alongside is given. Now, to find the point of inflation, guys, you have to find the second derivative and equate it to 0. Remember, when you find the turning point, you find the first derivative and equate it to 0. But when you find the point of inflation, you find the second derivative of a function and equate it to 0 to solve the x-coordinate of the point of inflation. So we're going to do nothing here but to find the second derivative of g at x. But first, let's find the first derivative, which is equal to 3x squared minus 6x. By that, when you have the first derivative, when you equate it to 0, you are going to find the x-coordinate of the turning point. Hence, you know that at the turning point, the derivative of a function is equal to 0. So at D and at B, the gradient is equal to 0. So that is why the first derivative is equated to 0, because the first derivative is just the gradient of g at x. Now, let's go for the second derivative of g at x, which is g prime prime of x, which is defined as 6x minus 6. Let's now equate that g prime prime to 0, because we know that at the point of inflation, g prime prime, which is the second derivative of g, is equal to 0. So by that, we are going to equate 6x minus 6 is equal to 0 to find the x-coordinate of the point of inflation, which is defined as just 1. So what do we do with this point after we found it? We substitute to the original equation to obtain y value. So our g at x is defined as x cubed is equal to x cubed minus 3x squared. So we are substituting the value x in the place of x. Then therefore we get the corresponding y value, which is -2. So we can show our point on the graph, which is 1 is to -2. This is the point of inflation. Remember, this is the first method of how do you find the point of inflation. Done. Then let's go for the second one. The point of inflation. What do you notice? You have the x1 and x2. Suppose x1 and x2 are the x-coordinate of the turning point. So how do you find the x-coordinate of the point of inflation now? Is to find the midpoint of the x-coordinate of the turning point to find the x-coordinate of the point of inflation. x1, which is the x-coordinate of the turning point, x2, which is another x-coordinate of the turning point. Then when you divide these points by 2, then you are going to get the median, which is the x-coordinate of the point of inflation, which is going to defined as just that. So the point of inflection coordinates is going to be, this is our x, and this is our f at that x, which is y. So we have found the point of inflection using that one. So there is a typical example in using that. Let's have this graph and try to apply this method. Now, let's say we have x1, which is the x coordinate of D, which is the x coordinate of the turning point D, and x2 is the x coordinate of B, which is the x coordinate of the turning point B. As you can see, x1 is equal to 0 here, and x2 is equal to 2 here. So by finding the midpoint of this x1 and x2, we are going to get the x coordinate of the point of inflection, which is 1 in this case. And you can see this one is the midpoint of 0 and 2. And when we plug it to our function, we get the corresponding y value, which is -2. We are done with the second method of finding the point of inflection. Well, let's come to the third one. Let's have this mother function, which is f at x is equal to ax cubed plus bx squared plus cx plus d. We are familiar with this one, and we are familiar in finding the x coordinate of the point of inflection, because we find the second derivative of our function and equate it to 0 to find the x coordinate. So here as well, we are going to find the second derivative of this function. Now, the first derivative is defined as f prime of x is equal to 3ax squared plus 2bx plus c. We are not done because we are looking for the what? The point of inflection, which means we need to find the second derivative. The second derivative of f at x is defined as f prime prime, which is equal to 6ax plus 2b. This is the derivative of this first derivative to find the second derivative. Now we are in a point of being able to equate f prime prime by 0 and solve the value of x. So after that, we take this 2 to the other side and change the sign of it. Then therefore, we are looking for the value of x. This x we are going to get is the x coordinate of the point of inflection. Let's divide by 6a both sides. You can see that we have negative, we have 2b divided by 6a. So we can now try to substitute. 2 goes to 2 once, 2 goes to 6 3 times. So this is what you're going to have after that simplification. So this formula is giving you the x coordinate of the point of inflection of a cubic function. Then to find the y coordinate, then you have to substitute to the x value, which is f at x is equal to the y value. This is the point that you have. After finding that, this formula you can just use without finding the derivative of g at x, finding this, it is already derived. It's negative b over 3a. Where is b? B is the coefficient of x squared, and a is the coefficient of x. If you know these coefficients and plug them in this formula, you are definitely going to find the x coordinate of the point of inflection. Then how do you find y? You substitute to the original equation, as you know. Done. Now, let's try to apply this in a real life scenario. What we have this f at x equal to ax cubed plus bx squared plus cx plus d. And our g at x is defined as 1x cubed minus 3x squared. And our a is just 1. Our b is just -3. So we know our formula. We have x is equal to -b over 3a. So us is to just substitute. In the place of b, we put -3. In the place of a, we put just 1. So by simplification, this negative and this negative gives you positive. and 3 divided by 3 is just going to give you 1. So the x value is just equal to 1. This is the x coordinate of the point of inflection. Therefore, you can write your coordinates in the form of 1 is to f of 1. Then you are done. Now, let's come to this one, because I want us to also be familiar with the analysis of the graph. Let's have this equation, this function, or this graph of a cubic function. The shape of it is telling us that the value of a is greater than 0, because if it start to have the maximum and the minimum, it means that the value of a is greater than 0, which means the value of the value of the coefficient of x cubed is greater than 0. Now, what else do you know? You know that the second derivative at this point D, if D is the point of inflection, is going to be equal to 0. The second derivative here is equal to 0 to find the x coordinate of the point of inflection. Now, in this portion, before A, the graph is increasing. You can see the graph is just increasing smoothly. The graph is increasing up to close to A. Then what else do you know? Then after A, the graph starts to decrease. It decreases up until it reaches close to B. Then you can see the F is decreasing. Function itself is decreasing. Then what else do you know? After B, the graph starts to increase again. If you are looking for the interval where the graph increases, which means after B and before A, this graph is increasing. So you can write in terms of x, an element of this certain interval. Let's talk about the gradients. The gradient where the graph is increasing is greater than 0. We know that when the line increases, the gradient is greater than 0, which means the gradient is positive. M is greater than 0 there, which is the derivative is greater than 0. Then when the graph decreases, we know that the first derivative, which is the gradient, is less than 0 because the line is decreasing. And of course, to this one, the graph is starting to increase again, which means the derivative or the gradient of that portion is positive, which is greater than 0. And of course, what do you know here? This is the turning point. The gradient is always equal to 0. And at B as well, the gradient is always equal to 0. You can see that. Now, if I am to explain the concavity now, if I am to explain the concavity, this is the point of inflection. This is the point of inflection. On the left, you get this parabola. Can you see this parabola? This parabola up until this point D. This is the parabola that is concaving downwards. This is the parabola that is concaving downwards. And the second derivative in this side is negative. Whatever value of x you can put in the second derivative of that function is going to give you a negative number because the graph is concaving downwards. Now, after B, which means on the right, this graph is changing the concavity now because it was concaving downwards all along. Then now, after B, it changes the concavity now. It's concaving upwards, which means this is another portion of a parabola, which means you can say the cubic function is just the combination of two parabolas that are going to meet at a certain point, and that certain point is called the point of inflection. And that point of inflection is where the graphs are going to change the concavity to allow the shape of the graph to point to or to face on the other direction. So now after D, you can see now the derivative, or the point, or the second derivative is greater than 0, which means whatever point you can put in the second derivative is going to give you a positive number, because the graph is concaving upwards after D. But before D, the graph was concaving downwards, which means the second derivative is also helps you to discuss the concavity of a cubic function. By that, I want you to like the video, and yes, please, as well, please do not forget to subscribe. Please don't forget to subscribe. And on that note, I'm going to create more videos on different topics. Please stay tuned, and you are going to be updated when the other video is coming, when you keep on subscribing. Thank you guys. Please enjoy.